think we can get started. All right, welcome back from the coffee break. I hope everybody had a nice tea and the milk biscuit, which is delicious. So my name is Sanghwa. I am working at Jefferson Lab, and I was asked to give a talk on the Hadron structure experiment for 3 lectures. So I really want to thank organizers for inviting me for giving these lectures. This is actually my first time visiting India, which is very exciting. And I'm looking forward to see more. After I finish my lecture tomorrow, I'll be more enjoying around here. But as you can guess from the title of this talk, saying it already tell you that I'm an experimentalist. And I heard most of you are actually theory students, and 4 of you are experiment students. Can you raise your hand if you're experiment students? So I can. Okay, I know where you are now. If I ask questions, and you guys expect to be answered. Okay. All right. So a little bit of my background. I did my PhD research at Brookhaven National Lab. Did anyone heard about it now? Since EIC will be there, everybody know where Brookhaven is? Good. So I will also show a little bit about the facility there. So I did my research there for PhD on the spin structure of the proton. So Brookhaven has this PP collider that has the polarized proton. Actually, this is the only polarized proton collider in the world that you have. And after my graduation, I actually moved to Jefferson Lab, which is the fixed target experiment. So we'll talk a little bit more about the difference between the collider and fixed target during this talk. So here I have collider and fixed targets. They have a very different energy and different experimental setup. But with these different machines, what I do is actually basically the same. I study the Hadron structure. So in these 3 lectures, my plan is to discuss the followings. For the first part, I will introduce you some basics of the hot scattering experiment, since most of you are theorists. And I do believe that whether we are theorists or experimentalists, if we know, understand the data and how experimental is done, it actually helps you quite a lot. So understanding your data that you're working on, especially you're a phenomenologist, then you understand the schematics of the data that you are trying to feed and extract the PDFs, for example. So that can really help you. But I won't go to technical details, but rather try to introduce you the working principle of the different parts of the experiment. In the second part, which is tomorrow, then I will start discussing on the measurement itself from different experiments. I will first start with the collinear observables, and then move on to the beyond collinear observers, and then discuss a little bit more about the future facility and the experiments and so on. All right, so let's get started. So when we talk about the nucleon structure study, it's really effort from the both experimentalist and also the theoretical side. And over the decades, there's humongous efforts there that push our knowledge forward. And for that, we have not only the inelastic scattering that we've been discussed a lot throughout the lecture the last couple of days, but also some other processes like semi-inclusive and hadron collisions, like PP collision or dual-Young process. All this together come in as complementary data sets that enhance the knowledge of the structure of the nucleon. And this having these different complementary data sets is also task of the very important part of the QCD, which is the factorization and universality. Means when you have the PDF from the DIS, you should be able to predict the physics from the other process, such as the hadron collisions. So the research for the experimental side has been done in various facilities For hadron structure experiment, we need 3 different components, which is the first, we need a probe, which is a beam. It can be a lepton or it can be a hadron. Of course, you need a target. That's what you are trying to prove. It can be another beam. In that case, you will have a collider. And it can be another fixed target. And then lastly, you need a detector to detect and analyze what's produced from the collisions. So we have accelerator, which produces a beam as a probe, and have a target. It's an example of the target at Jefferson Lab for the polarized helium-3 target. And then the detector here. So let's discuss one by one a little bit. All right, for the first accelerator. So here, there are many different types of accelerator in the world. But if you look at the list of the particle accelerator, if you Google it, then you will have a very long list there and for different performance parameters and so on. Here we only discuss the places that are most relevant to our topics. One is SLAC, the linear accelerator, and Jefferson Lab, and everybody know the Large Hadron Collider at CERN, right? And the HERA that we've been talking about a lot throughout the lecture so far, which was the EP collider. Fermilab has the Tevatron and also the fixed target experiments there. And Brookhaven has a PP collider, and then the E plus E minus collider in Japan. So just briefly, just introduce you how those other different accelerators are. So first, the SLAC is the linear accelerator that out of all the accelerator I'm discussing in the this talk, this is the only linear accelerator that we'll talk about. And later, throughout the upgrade for many decades, it also has a E plus E minus collider for other physics. But for us, most relevant thing is this from this fixed target experiment that has this major physics discovery for hadron structure about the evidence of the quark structure inside the proton, which won the Nobel Prize in 1990, which is like more than 20 years later, actually, after the experiment. That took a while. But besides that, total 3 Nobel Prize was won at SLAC, including the time quarks that was shared with the Brookhaven discovery, as well as the tau lepton quarks. And another electron facility for hadron structure is the CBAF. It's a continuous, let me see, electron beam accelerator facility. I should know this because I work from there. It's at the Jefferson Lab. Jefferson Lab is in Virginia, also in the United States. And you can see from this area, this chart here. Here you can see this accelerator, the beamline structure here, right? And then there's you can see this tiny hill at the end here. Those are where the fixed target experiments happen. You can also see from this schematic view here. The Jefferson Lab usually ran at 6 GB in the past, and recently has upgraded the energy to 12 GB. As I mentioned, that there are different the experimental hall that study the different aspects of the hadron structure and or the hadron spectroscopy as well here. And here, HERA that we talked about a little bit so far, and days in Hamburg. Operated in 1992 and 2007, it has this HERA collider, and there's 2 collider experiments, which is one is H1 and the other is JIVS. There's also fixed target experiment in HERA. One is Hermes. This was using the electron beam and to study the polarized structure of the proton. And the HERA-B used the proton beam to study more heavy quarks. And so HERA, I can see here, it has very large, the ring there, which is 6.3 kilometer and you can have energy of proton up to 92 GeV and the electron 27.5 GeV. The interesting about the Hera is that the electrons was self-polarized. You know what self-polarized means? Anyone? All right, so normally in other facility, if you want to have some polarized beam, it normally comes with the, for example, for the proton collider, you have an injector that already has a source. For example, CBAP here, it has polarized electron, and you start from the injector that's already polarized electron. But Hera had this self-polarization from the effect of the synchrotron radiation emission. So when you have this circular ring, this is only when you have a circular ring, when you have this magnetic field to bend the beam there, right? And when you have the magnetic field direction, which is in this case, if you want to have the beam, it will be vertical direction. So for the spin direction that is parallel or anti-parallel to the magnetic field direction, when it emits this synchrotron radiation, it may flip the sign of the polarization. So over time, the beam of the electron will start building up the polarization only in the vertical direction. So in this case, you are getting the polarization free, but it will be only one direction. Okay? So they had this polarization up to 60%, which is not bad. And if you think about it, that, okay, Hera has electron polarized beam and unpolarized proton collider. We are trying to build the EIC with both polarized electron and proton, right? For the EIC, you will actually have the source that has polarized electron source. And if you think about this effect, it will be still there because the EIC will have circular electron accelerator there, circular ring. So if you inject the electron beam with the polarization from the source, a certain high percent, this may slowly depolarizing your polarization. So what's going to happen is that you inject the polarized beam at certain high polarization, and then you re-inject so that you recover the polarization. And another interesting thing about this is that you can read about it in a bit more detail, because I found it very interesting when I started looking at it, that the spin flip probability for this effect is actually different from when it up to down or down to up. So depending on the polarization direction, particular polarization direction you have, the source, you may have a different frequency to re-inject to keep your polarization. Think about this, and then you can talk about more later if you're, and there's also the EIC director sitting here, and you can ask more about this in detail. All right, moving on from here. So now we talk about liberal polarization, and when we talk about the Hadron structure, it's not only the unpolarized structure, but it's also we study the spin structure of the proton. So at LHC, this is Large Hadron Collider, but the experiment we are interested in here in this talk is using this SPS beamline. This is super proton synchrotron beamline. And from here, from the proton beam, you can produce the other hadron or muon beam, and that's what it used for so-called compass experiments with the muon beam, and has the polarized gas target and study the spin structure of the nucleon. Okay. And then here, the relativistic heavy ion collider at Brookhaven, where the EIC will build. But until then, it will still serve as the polarized proton-proton or proton-ion or heavy ion machine. So the rig has the polarized proton and ion collision capability. You can have the transversely or longitudinally polarized proton. But the polarization at the source will be always vertical direction, because it's beneficial in the circular link to have it keep it in the vertical direction. But we also study longitudinal polarization or longitudinal structure of the proton. And there was some question yesterday, I think, about when you have the polarization, the beam, how can you actually measure it, right? I don't know if it's addressed during the discussion, but we'll talk about this later more when we talk about the result from the rig. And it has proton beam polarization up to 55%. And there's two main experiments, which is the Phoenix and Star, and that took the data for more than 10 years for both transverse and longitudinal spin structure. I'm almost there to finish accelerator here. So another one is the Fermi accelerator. There's a Tevatron here, which is the proton-antiproton collider there. You can have energy up to 1 TeV. That give you total collision energy about 2 TeV there. It's famous for its discovery of the top quarks, but our interest here for our topic for hadron structure is rather on the fixed target experiment happened at Fermi Lab. So the main injector ring here, which can have 120 GeV up to, can send the beam and produce the hadron beams using some other target. And then from there, one of the experiments, you can have the neutrino experiment that you send the neutrino to the very, very far away underground and have some hadron beam for testing the detector, which is very actively happening for many years. The experiment that we are interested here is actually the fixed target experiment using which is called the Drell-Yang experiment. And this one is quite interesting process to study the C quarks. And we will talk about this when we talk about the C quarks. Lastly, the E plus E minus collider at the KK in Japan. And it has the electron and positron beams with the little bit different electron and positron energy. So it has asymmetric energy. And why would you want to do this? Think about it. The KK had actually the fixed target type of the detector here. So if you think about this asymmetric energy, why would you want to do that for this type of study? And I'll ask you later. So it's actually the so-called B factory because it produced the B quark hadrons to study the CP violation, some other physics processes. We'll mainly discuss about this in terms of the fragmentation function study. Okay. So all right, so we've been talking about different particle accelerator, collider, fixed target. So there are two types that we've been talking about, right? There are difference, of course. The main difference is the energy and luminosity. And also depending on the type of experiment, you need to design your detectors and experimental setup differently. For example, the collider, as we talk about it, has two beams. The advantage of the collider is it can achieve the high energy. And since the interaction point is here and you have a head-on collisions, the detector, the apparatus for the experiment, is normally surrounding around the interaction point with the onion structure. The fixed target, this is one of the examples in the SLAC experiment, has a single beam and with a fixed target. It can be gas target, it can be liquid, it can be solid. And as I mentioned that, and when you think about the particle physics, everybody just want higher energy, right? So why would you want to do that then fixed target experiments? What's the advantage of it? I mean, of course, there might be some other advantage to look at some specific experiment or process. And one of the big advantages of the fixed target is the high rate. If you think about the target you are using, if you're using solid target for sure, compared to the using other beam together, you will have much higher collision rate. So it's good for precision study, because you can get lots of data. Or if you are looking at the rare process, where you really need to have luminosity, and this is good for you then. And you can see the experimental setup here is covering this boosted forward region because of the asymmetric collision feature. So the two parameters that we talk about, important for the accelerator, these are the parameters that characterize the performance of the accelerator. One is the center of mass energy. We talked about a little bit from the previous lecture. So center of mass energy is basically the energy you can have a maximally achieved in a collision. So for the center of mass energy, when you think about the invariance, the quantity, which is the total for momentum square of the system, and you can actually write down the center of mass energy in terms of this left frame quantity and calculate the center of mass energy here. Normally, you can approximate to this two energy of the beam and target, and you usually use this square root to S quantity here, which is the actually center of mass energy here. Of course, for the collider, if you assume the head-on symmetric collision, your energy will be just twice of the beam energy. But for the fixed target, your center of mass energy will depend on both the energy of the single beam and also the target of the mass of the target. And as you can see here, there is a square root term here. If you think about the fixed target, why it's hard to achieve the higher collision energy, and here's your answer here, right? So let's look at some example. So for the RIG PP collider, you can have a proton energy up to 250 GeV. Then what's the center of mass energy here? You have a 250 GeV proton collider. Your center of mass energy will be then 500 GeV. Yes, you simply just add them together. That's 500 GeV. For HERA, electron beam energy maximum is 27.5 GeV, and proton beam up to 920 GeV. What's the center of mass energy? A little bit of calculation, hopefully. You can just ignore the mass term actually because the energy is much larger. You can approximate it there. The answer is about 320 GeV. So now, other question is, if you are actually designing the EP experiment with a fixed target setup, but you want to have a same center of mass energy as HERA collider, what would your beam, assuming electron beam, energy should be? To have a similar center of mass energy as its collider from the fixed target with electron beam, how much electron beam energy do we need? Can you guess, just roughly, how large it should be? Yeah, just a rough ballpark, like 10 times more, 100 times more, 1,000 times more. All right, the answer is about 50 TeV. So it's not going to happen during my lifetime to have the fixed target with the 50 TeV beam. So we better have this EP collider, right? All right, so the other parameter that's important for characterizing the collider performance is luminosity. So luminosity is basically here, you have a scattering rate and then cross-section, and the ratio factor is this luminosity. When you think about the scattering rate, when you design the experiment or think about the measurement, you need to know what's the rate you will get, because so that way you design your experiment, determine the DAQ configuration, for example. This cross-section is given by physics for the process you want to, but luminosity is given by the setup, later and how you set up the experiment. So basically, luminosity is if you have a more beam particle, more target particle, and you will have a higher luminosity. Makes sense? Because you have a more collision probability, right? If you have a more thing throw together, there's a higher chance they will scatter to each other, right? So basically, that's it. So for fixed target, if you think about the more beam particle means you have a incoming beam flux is larger. More target particle means you have larger target number density, and you can have a thicker target. That way you have a more. So that you can characterize in simple form the fixed target luminosity. The collider, because your target is another beam, and normally your beam is in a bunch structure, So you have this bunch structural beam, and each bunch has a certain number of particles. So your luminosity will be then depends on how many particles you have in each bunch, right? And how often you are colliding them. It depends on the frequency of, and also if you have the bunch that is very spread versus very focused, you have different luminosity, right? More focused beam will give you higher luminosity, but it's pretty hard to make the very focused beam if you think about to put all the charged particles together in a very tiny profile. It will depend on the beam profile as well. There are actually other parameters or factors goes in to determine the actual luminosity. And in collider, for example, for EIC, there are some factors that limit how high we can go for the luminosity as well. For example, the synchrotron radiation for the electron beam will limit the electron beam energy, for example. And here it shows the luminosity and central mass energy, the two parameters that we talked about it, and for different experiments. You can guess what's in here very high. This is what type of experiment? Collider or fixed target? Fixed target, right? So you can see the high luminosity here. And Hera as a collider compared to fixed target, much larger central mass energy here. And EIC has higher luminosity than Hera and slightly lower, but has some overlap of central mass energy coverage. And here, compass here actually also fixed target. You can compare this luminosity, they're different. Think about why, okay? And come back to me if you have an answer, okay? All right, so I will define one more variable related to the collider, which is called rapidity and pseudo rapidity. This is not a parameter that you would be familiar if you're from the fixed target background, but very commonly used for the collider. So it is very convenient variable to define. It's defined as the energy and the longitudinal momentum of the particle. And for high energy collisions, the difference between two particles of this rapidity is invariant under the Lorentz boost along the G axis, because the beam goes in G axis. So it makes it a little bit easier when you do some calculation. But more commonly, we define so-called pseudo rapidity, which is only then depends on the angle theta. And as an experimentalist, we use this a lot related to how we design the detector configuration, for example. And this is also easy to measure since you only need to know the angle and directly relate to the detector, as I mentioned. All right, so since we started talking about a little bit of detector, let's move on to some topic of detector, how we consider detectors. From the point of view of the physics process that we consider, for example, from the DIS type, we have inclusive measurement that you need to measure scalar electron, right? So we only care about measuring scalar electron in principle. If you know the momentum of the scalar electron and what was energy for incoming beam and target, then you're good. Semi-inclusive interaction measure on top of the scalar electron, but also final state hadrons. And when you measure this hadron, you also want to know which hadron you have there, so that you can relate that to the flavor of the quarks, for example. In that case, you need to measure scalar electron and hadrons in coincidence. And there is exclusive measurement that require more stringent condition for measurement, which you need to, in principle, measure all particle in the reaction. So with this, if you want to measure electron, well, for inclusive measurement, which is important, you need to measure electron. You need to be able to say, this is electron. And measure the energy and momentum and angle. For semi-inclusive interaction, you need to measure the hadrons. You need to have a good hadron identification and also have a wide kinematic range and coverage. And for exclusive measurement, you want to measure with the very large aperitif coverage to detect the recoil and the target remnants. and also neutron detection. Okay. With this, let's relate to some basic about the detector. So the basis of the particle detector is basically from the interaction of particle with matter. The matter is the material of the detector, basically. So you want to know energy, momentum, position, type of the particle that produced, and you just make it interact with the material there. For the long-lived particles with lifetime larger than about 10 to minus 10 seconds or 10 to minus 10 to 12, you can actually do this. But there are not many those particles. The short-lived particles, they will decay very quickly. For example, pi 0 will decay to 2 photons. Its lifetime is 10 to minus 18, for example. But you can still measure this from measuring this decay product. If you measure the 2 decay photons from the pi 0 and deconstruct the invariant mass of it, then you can identify pion. There are also undetected particles, for example, neutrino. How do we measure this? You can do that by measuring everything and then deconstruct missing mass. What's missing? And that's neutrino this way. Okay? All right. So now talk about a little bit of interaction of particle with matter. This is the basis of how you actually develop the detectors. So I'm more focusing on the aspects of this, what's the working principle for different detector, because you can easily see what kind of other detector available there. But since most of you are theorists, I thought this might be more interesting to discuss. So for the charged particle, how it loses energy, for example, one way is from the ionization. The charged particle goes through the matter and then ionize the atom and lose energy. So this is important for all charged particles, and it's dominant from this Coulomb scattering from the atomic electrons. And it can be characterized how much energy loss it is by this Beer-Bloch formula. It's very well known for experimentalists in particle physics. So this shows the so-called DDX, the energy loss, versus the momentum here. You can see here there's curve for different the material, but all have the similar structure of the curve. So here, if you relate this at this region where you start having a little bit higher velocity, for quickly because of this term here. But over here, you can see there's a sort of a minimum for different material. This is called the minimization value or minimization particle, MIP. And they are normally around like 2 GeV or so for most of the relativistic particles. And after this, for a larger momentum, where it's just slowly rising because of this logarithmic term. And with DDX here, and this is this energy loss is the basis of the most of the gas tracking detector, gas detector. But also you can use this DDX for particle identification. Because if you know how much energy it's supposed to lose for a different particle, and you can basically then relate it to that. For example, if you have a momentum measured from your tracking, and with the DDX, how much it lost, you can relate it to what's the mass of the particle, and therefore identify what particle it is. Right? The other process for energy loss for the charged particle is radiation energy loss. So you have a nucleus in the material of the atom. It has electric field, produce electric field. And when charged particle pass by, you can accelerate it or decelerate it, depending on which direction is coming in, approaching, going away. So from this acceleration or deceleration, the particle then radiates photons, right? This is called Bremsstrahlung. I always have a hard time to actually pronounce it. It's actually a German word, and it means actually breaking radiation, very direct. And this is particularly important for electron and positron. It's become basis for the calorimeter detectors. So the energy loss for the electric electron depends on the so-called radiation length. This is the parameter that's different for the different material you are using. So, energy loss of the photon and electron, as I mentioned, is the basis of the building the colorimeter detector. The colorimeter detector is you need it for measuring the energy, and this is, in this case, this is the electromagnetic colorimeter. The dominant process for electron, as I mentioned, is Bremsstrahlung. And as you can see, this energy loss is depending on energy of the particle, and this x0, this is radiation length of the material. And for the proton, its probability for the absorption is actually pretty high. So from the absorption of proton, we produce electron and positron pairs. This is the dominant process. There are other processes for the more lower energy, but here the pair production is dominant for energy larger than few MeV. And again, the cross-section or the probability for pair production depends on this radiation length. So what happens when electron and proton pass through the medium? For example, electron, it produces photon from radiation energy loss. And photon then produce electron and positron pairs. And then one of the electron here, for example, emit photon again. And it produce pair and electron pair. It produce this cascade of the electromagnetic shower. So this is how it loses their energy. It means it deposits the energy of the particle of itself, and we can then convert this to the signal and measure its energy. And that's the colorimeter detector. Okay? All right, so the next one for the detector type is the particle identification, which is basically velocity measurement. And this is important, as I mentioned, especially when you need to measure the final state hadrons. And depending on what your requirements, what's limitation, how your detector arrangement, how much space do you have, then you can choose which detector to choose based on which process. Okay? So there is Cherenkov radiation, time of flight, transition radiation, radiation energy, we talked about it. So one is a Cherenkov detector. The Cherenkov radiation is when you have a charged particle pass through medium. And if the speed of this particle is faster than the speed of light there, then it will emit the Cherenkov radiation there, right? So it only happens when the velocity or the beta value is larger than 1/n, which is the refractive index of the medium. So you can also then say that this is the threshold value for Cherenkov radiation to happen, right? So when Cherenkov radiation emitted, it produced this form of radiation. And this angle can be defined this way. So you can use this detector for two different modes, largely. One is threshold mode. Basically, looking at this threshold, different particle will have different threshold, right? So in this case, you just count the number of photoelectrons produced. If the momentum of the particle is less than the threshold value, it's not going to produce any Cherenkov radiation, right? So depending on the particle type, you have a different threshold, right? And the other method is using so-called ring image Cherenkov. You can see here again, you have this Cherenkov angle, and this you can see here, this is ring structure here. If you project this to the flat surface. So from the momentum measurement from tracking and measuring the angle, then you can reconstruct the particle mass and therefore identify the particle. You can either have a gap and then make this naturally form this ring here, or you can use a mirror to reflect it, or use a lens to form the ring in the detector surface. Okay? And the other type is called time of flight. It's basically if you know the distance from the interaction point to the detector, and you measure that, and how much it took to travel, then you can basically then know the velocity, and therefore relate to the mass of the particle and identify what it is. The important parameter that determines the resolution for time of flight method is, of course, you want to have a longer distance so that it's easier. But it is this, the timing resolution of detector. if you have, let's say, a certain distance, fixed distance, because your detector will be sit somewhere from the interaction point, so your distance is fixed. And what we characterize the performance of this type of detector is so-called separation power. So if you want to separate the pion electrons or pion and kaons, the minimum normally we require is 3 sigma. But normally we want a little bit more for the more stringent measurement. Let's say 3 sigma. And for pion electron here, but let's look at the Kn pion. And if I have a 2 GB kaon pion and want to separate by 3 sigma, and I can just have a 100 picosecond detector. If I want to have 3 GB, then in this I should have 60 picosecond of time resolution in order to have the resolution that I want. Okay? So more resolution or higher momentum reach you want to have, then you need to have a better time resolution for that. Okay? All right. So all this together, the detector normally in the modern experiments has multiple systems and therefore has this onion structure. You have a tracking, colorimeter, and PID. And normally the colorimeters are destructive because it deposits all the energy, supposed to deposit all the energy. Therefore, we can measure the energy of the particle. But tracking system should come before, close to the interaction point. And then colorimeter goes normally more outer side of detector. Muons normally don't interact much with other material. So whatever deposits the energy and whatever left after humongous material is muon. So muon detector, you want to have most outer region of the layer of detector. Okay. So how it looks like in the detectors, and actually, this is for C spectrometer and detector package here. You have this onion structure. I have a drift chamber, which is tracker, and then there's PID, and you can see the colorimeter here is all the way in the back. This is star detector from the collider, so you have this more symmetric structure around the interaction point, and most inner side, you normally have this tracking detector, and more also this other tracking detector here, and then the colorimeter after that. And this is how the EIC detector will look like. You can see something similarity from already. Inner side, this will be tracker, right? And then there is colorimeter, and then Hadron colorimeter will be sit outside. All right, so we have so far reviewed the tool for Hadron experiments, accelerator, and detector basics. So with all this together, now let's start talking about the measurement. So we have talked about the measurement of the inelastic scattering. And so far, we keep saying that we want higher energy, right? Why do you want higher energy for a particle accelerator? There are a couple of reasons I can think of. One, for example, if you want to look at the particle that only produce at higher energy, for example, like a W or G boson, then you need high energy. The other is that if you want to prove something more inner structure, you have a better resolution, then you need a higher energy. If you think about, like, I have my hand here, and if I look at this underneath my skin, or if I have some ankle injury, I want to look at underneath of skin what's going on there. What do? You go get X-ray scan, right? So you have used very short wavelengths probe to look at more smaller scale of object. So studying the substructure depends on how you see things, right? Similarly, for the Hadron structure, it depends on how we see it. More other expression, how we hit it. Okay? So if you have the electron proton scattering with a smaller Q square, you may have elastic scattering, and from there, you measure form factor. We discussed in the previous series of lecture. And from there, you can actually extract the charge density of the proton. And this tells you size of the proton, basically. If you have a higher Q square, you can see already the wavelengths much smaller. You have inelastic scattering, and you can measure here structure function, which contains the information of the proton structure we have discussed so far in the previous lecture. So energy matter, right, to study more small scale, short distance interaction. So higher energy has been leading us to the discovery for the Hadron structure. One is Rutherford scattering in 1910s, around there. This is one of the first fixed target experiments. What he used was the beam of alpha particle with the 5 MeV energy, MeV, we're talking about MeV. And this is a beam. You need 3 things. And then gold, very thin gold foil. You have target. And then you need a detector. He used this scintillator counter. So basically have some scintillator material, and then looking at the scintillator light that's produced, and then count it. For example, he's looking at it here. This is geyser. From this, he discovered that there is point-like charged region inside of the atom, right, nucleus. In 1954, Hofstadter did something similar experiment with the electron beam now and nucleus, hydrogen, or proton or neutron target. And then this time, he used the electron beam as a probe instead of the alpha particle, and used a 200 MeV beam, much higher energy compared to 5 MeV if you think about it. And his experiment setup looks like this. I have a beam, target, spectrometer. The basic structure is basically the same, right? And from this, he tested if the proton is a point-like particle or it has finite size. And he discovered it has finite size. And later in 1967, finally, at SLAC, MIT experiment used the 4 to 21 GeV beam, electron beam, as a probe. And with this hydrogen target, for example, to study proton. And did experiments and discover for the first time experimentally that quark structure of the proton. And all these 3 discoveries led to the Hadron structure and the Nobel Prize from their discovery here. You can see the energy matters, right? So this is the SLAC experiment, one of the visual there. And what you actually measure is the cross-section from this interaction. And compare with this mode scattering cross-section, basically you assume the point-like scattering. And you scan it over different momentum transfer. And if it's elastic scattering, it will be like this. What comes out as the data is like sort of flat, right? So what it tells you is that it has collision with a point-like constituents inside the proton, okay? Instead of the diffusive distribution of the charge in there. So some decades later, we still do fixed target experiments, but does it look modern compared to the SLAC? It looks about similar. We have a beam here coming in, target and spectrometers, right? This is Japanese lab for A. The class experiment at JLab and a compass experiment at CERN actually have these spectrometers right at where the target chamber is. So if you think about the EP collider, and if you think about make one of them as fixed target, and your detector will be then has to be in boosted region in the front, and that's where the detector is sitting here. So the divisional scattering that we've been talking about a lot, I won't go through much details, but the introduction has been given multiple times. We measure the cross section and determine the pattern distribution functions from the fact that it can be factorized between this short distance and long distance interaction. And these extracted pattern distribution functions can then be used for predicting other process, like for example at the LHC, or this cross-section of different PP scattering interaction using the PDF that's extracted from the HERA. You predict the cross-section, and it has been very successful. So this tells you the prediction power of the QCD. I was too close to the conclusion. All right. All right, so what we measure from the inclusive DIS is this cross-section and extract this structure function that we discussed. And from there, relate to the parton different functions. We can polarize it and then measure the polarized structure function. This will tell you the spin structure of the proton that we will discuss in the later part of the lecture. So HERA was really ultimate DIS machine so far. And these collider experiments, H1 and GEOS, this is the H1 detector. And again, you can see this onion structure detector. And then GEOS, they look very similar, but there are some differences that make them very complementary and strengthen the program. So this is one of the example of how EP event looks like in the event display of the H1. So this is detector here. There's electron coming in, proton, and one of the inclusive interaction, there's scattering electron here. And you can see here in the event display, here the deposit energy in the colorimeter. So this way you measure the energy of electron. You identify the electron here, scattering electron. There's hadron produced, and in here, there's a tracking in the most inner side. And then in the hadron colorimeter, it divides the energy here, also divides the liberal energy in the EM car as well, but mostly or in the hadron colorimeter here. So what you measure here, hadrons and also electrons. So HERA can actually allow you to measure this final state hadron, the observables, the parameters, the full momentum of it. From this, what we need to do is that measuring cross-section, when we measure cross-section and extract the F2 structure function, we want to measure the as a function of the x and q square, right? So we need to reconstruct these kinematic variables, x and q square. So, but those are not what you actually directly measure, right? What you actually measure is something like scattering electron energy, scattering electron angle, and hadron momentum, for example, and watch the angle of it. And from those detected variables, we want to reconstruct it, x and q square and y. So there are methods to reconstruct the kinematics. One is the using the scattering electron, or you can also measure or the reconstruct hadron recoil instead of the electron, and you can actually construct the ice kinematics from there. There are several methods to reconstruct this YQ square and X, and some of the most classic reference for this from HERA is this paper. So there's a detailed discussion there. But here, one of the most simple methods for the inclusive DIS is you just measure scalar electron, its energy and angle, right? But there are more here in the table here. So there are actually more than this, but I only discuss, compare some of this only here. So here again, your detected variables. Here we define in HERA that the quantity that's the summing over or the hadron energy and longitudinal momentum, and also this the transverse components and define the variable something like a transverse momentum of the hadrons, and you can extract this, reconstruct this. And different method use only the two of the variable from here, or three, the two, and then electron energy, instant energy, and then you construct y and q square differently, and then x can be reconstructed from those two, right? There's advantage and disadvantage between the different methods, and that's also led to the kinematic visions and detector performance. If you have a really good electron energy measurement, then electron method will actually perform really well, which is most of the case for DIS type experiments. So for example, for GEOS had really good hadron colorimeter. So for kinematic construction GEOS, they use hadroning method here. For H1 had a better electron measurement. So they use the electron method and some other so-called the sigma method. And here, this hadronic method, actually, if you look at it, they don't actually need to know anything about the electron, scalar electron information. So if you have some region that have acceptance that you can really measure the scalar electron, then you can use this hadronic method. And for the charge current also, you can only use the hadronic method. Right. And recently, there has been some development of using the machine learning technique to reconstruct the EIS, for the EIC. I will not discuss here in talks, but I post the one of the paper that was recently published. So when you reconstruct it, here, you compare them. So for example, this is from the HERA study. And here what you're seeing is a different method. Here, the one is electron method here, right? And hadronic method. And double angle, we only need to just have angles quantities here. And then this sigma method for sigma method. And you compare them for different region of Y for the Q square rather than 7 GeV, for example. You can see from the electron method here, for the larger Y region here, compared to other method, it performed really well, right? But if you go to the smaller Y, if you remember this electron method, actually, the measurement Y in the small region will have this term that's smaller, then it's going to have a worse resolution there. So that's what you have this worse resolution here for electron method here. The hadronic method normally perform better around this smaller Y region compared to the electron method. And the sigma method is overall doing pretty well for the Y region. So you can decide which one to use depending on your performance limitation detectors or kinematic region that you're studying. Okay. All right, so I will stop here. But the later part, or come back to here a little bit, but later part, we will actually start discussing about this measurement and observable that we had in the different machines that we discussed so far. So we will start with the HERA measurement briefly and a little bit discuss about the extracting the PDFs from the experimentalist point of view, more in a more practical sense. But that's not the end of the story. We'll discuss more about, so far we talk about reaching to the lower X, right, with higher energy. But how about the larger X? When we talk about the PDF, we don't really looking at very larger X region, but there is actually very interesting physics there. And if you look at the PDF error from the PDF analysis in the larger X, you have this large error bar here because there's no data. So we'll talk about the larger X distribution in the next lecture. And in particular, what's interesting is this F2 structure function ratio. And how about the C-quarks? Okay, we'll also discuss about C-quark. This is an interesting result that came out a couple of years ago. And also, finally, we will start discussing about polarized structure. Okay, so let's finish here. And if you have a question, please feel free to talk to me. But if not, thank you for listening.